Hi, everyone. Welcome to our introduction to Chapter 4. In this chapter, we're going to see um, a lot of new ways to draw and to interpret our first functional group, the alkane. With the alkane and the cycloalkane, what we are looking at are hydrocarbons, specifically hydrocarbons that are all sp3 hybridized, fully saturated. They're going to be everywhere. So hopefully we'll be able to look at our hydrocarbons that are fully saturated, such as ethane or butane. We can think about cyclohexane. We'll be able to do a bit of naming. These are saturated because there are only single bonds. So if you've heard the idea of a saturated fat, that means that it's a hydrocarbon that has all single bonds. An unsaturated molecule is one where we have a double bond, a pi bond, or even a triple bond, 2 pi bonds. And so with unsaturated things, we'll start incorporating degrees of unsaturation where there's not as many hydrogens as possible, right? We have double bonds or triple bonds between different carbon atoms. We're going to see all the hydrocarbons, specifically alkanes this chapter. So we're going to be dealing with the saturated hydrocarbons. But we will start branching off once we get into reactivity. We'll start using the unsaturated hydrocarbons. Just to present some ideas of some common names. We use a lot of common names in chemistry pretty much because organic chemistry is relatively new when we think about the depth of science and the history of science. Many organic compounds have common names. Formic acid, this first one on the left, ants actually produce formic acid within them. And so when this compound was isolated from ants, they named it formic acid because of the Latin word for ant, which is formica. Morphine, I love the explanation for morphine here. Morphine, the painkiller, is named after the Greek god of dreams, Morpheus. So we can start to see how the influence is either historical or Latin. Barbituric acid was named after the guy's wife. Like, how cool is that? Very, very romantic to name a compound after your loved one. Excellent. We are going to be using the IUPAC nomenclature of alkenes. Again, IUPAC is a systematic way of naming. You might have heard IUPAC back in the day in general chemistry when you were learning naming of some ionic and covalent compounds. Now, for organic compounds, naming is a little bit different because we are dealing with hydrocarbons, because we want to make sure that this rule, this system of naming covers every imaginable type of compound. We're going to be doing a couple of other things. Now, typically when we look at some sort of an organic molecule, we got some branching, maybe we have a couple of things coming off. So looking at the skeletal structure, where do we even start with naming? I guess we could number, right? And that's the first thing that we would want to do is find the longest parent chain. Now, from our parents come offspring, right? That's what we're going to be calling substituents, things that are branching off of the parent chain. And we have to locate where those substituents are. So for me, I'm just going to quickly find that longest parent chain here. I'm numbering it just to be able to make sure, okay, is it 9? If I did 6, what about 7, 8? No, that's not the longest. 6, 7, no, that's not the longest. Starting down here wouldn't be the longest. So trying to find the longest parent chain, I've done it left to right. So this one's a little bit more straightforward. It doesn't always have to be left to right. And then finding substituents, finding carbons that I haven't numbered, that are branching off. I've got that 2 carbon group and the 1 carbon. Here's another 1 carbon. Here's another 1 carbon. Those are substituents. And where they are located means where are they on the actual parent chain? This one's on carbon number 3, this one's on carbon number 5, these are on carbon number 6. And that will be how we start to name this compound. We're really going to be breaking apart the molecule that we have, the hydrocarbon specifically, and being able to piece together different portions of it. What's really important is that we do this in a systematic way. We always want to find the longest carbon chain. We want to find the substituents, and we want to number the substituents so that we can actually converse and communicate the location of those. So those 3 steps are going to be the overarching theme that we'll see now in a whole bunch of examples. When we select a parent chain, what's really important is that we know how to name that parent chain. It's going to be the foundation of our nomenclature, the foundation of the name of the molecule. So we look to this chart knowing if it's 1, 2, 3, all the way up to 100 carbons, we can look at that and say that the parent is going to be either a meth, eth, prop, bute, pent, however, whatever we have in terms of the number. Now, I do want you to know 1 through 10. 11 through 100 is something that's in your textbook. I will not present 1 through 100 or 11 through 100. I'll only stick with 1 through 10. We can get into some really crazy structures. The parent is the prefix, and it's the root of knowing how many carbons there are. So 1 is always meth, 2 is eth, 3 is prop, all the way down to 10, which is dec. If we are dealing with an alkane, again, an alkane is going to be where we start our functional groups. It is going to be a fully saturated hydrocarbon. Generically, the alkane has the formula C to whatever value n, H to the 2n plus 2. So if you have 5 carbons, H would be 5 times 2, which is 10, plus 2, 12. So let's just get some of these structures out on my board. And I want to kind of give us not one that is tricky, but one that is maybe a little bit harder to find the longest parent chain for. So here's this guy. Now, when trying to find the longest parent chain, what we want to be able to do is count the consecutive carbons in a row. So start at an endpoint. Don't start at a middle. You want to be at an endpoint. So maybe I'll start here and go 1, 2, 3, 4, 5, 6. Well, I don't think that's right. I think there's going to be more if I go down. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Maybe 1, 2, 3, 4, 5, 6, 7, 8. Okay, that's not as good. 5, 6, 7. That's not as good. I think the one that I found here, 1, 2, 3, 4, 5, 6, 7, 8, 9, is my longest chain for my parent. So I'm going to go ahead and number those in green. Now, 1, 2, 3, 4, 5, 6, 7, 8, 9. This would be nonane. That's the parent name. Now, there are other substituents around that, right? So when we're looking at those other substituents, that's when we're going to start numbering those and identifying, here's 1 carbon, here's a 2 carbon chain, here's another 2 carbon chain, and here's another 2 carbon chain, right? All right, with naming substituents. Now, substituent names will always be very similar to the parent. The only difference is the substituents will have the ending YL. So when we're looking at naming of those substituents, a couple of things to consider. Let's just do a long straight chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. And then let's just put some things off. There. All right, so let me number or highlight my parent chain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Parent name, decane. That's my parent. Now, naming of the substituents. Naming of substituents is going to be anything else that hasn't been numbered yet, hasn't been highlighted. So we have this group with 2 carbons. We have this group with 3 carbons, and this group with 1 carbon. So in naming of substituents, we want to name them very similarly. Take the number of carbons and add the YL ending. So 2 carbons, eth-il, ethyl. 3 carbons in a row, prop-ul. 1 carbon, meth-il. So being able to look at those substituents now, after I've located the parent and I've located the substituents and named everything, all of the carbons should be highlighted. That's what we want to be able to see. And how we differentiate substituents from the parents get the ending ANE, the substituents get the ending YL. If the group comes off in a chain, in a very nice row, 1, 2, 3, that's our typical propyl group. Same thing with butyl, 1, 2, 3, 4, butyl. It's when we actually have the change or a branch in that continuous line. So being the parent right here, this would be any other group, whether it's a cyclic structure or just a longer chain. If you have this branch of 3 carbons where the second carbon is attached to the parent, this is what we call isopropyl. Now, when we see isopropyl, that is the common name for that group. You can use the systematic name 1-methyl-ethyl. There is 1 carbon attached to an ethyl group. But I like just memorizing that name, isopropyl. There's only 4 to remember. Now again, if we have that idea of 4 carbons where 1, 2, 3, 4, the parent is attached to the second carbon, sec-butyl. Sec for second. 1, 2, 3, 4. It looks like the same idea as the isopropyl here, just branched off at carbon 2. That is the isobutyl. And 1, 2, 3, 4. I call this one looking like the chicken foot. It's a tert-butyl group. So putting it all together, the last step was locate the substituents. So I'm going to do another structure here. There we go. And I'm going to start by saying, okay, the ring, the 5-carbon ring is my parent. That is my cyclopentane. I have a couple of substituents. I have a methyl, and an ethyl. Now I have to locate the substituents with a number system. How do I actually number them? I try to find the numbering system that results in the lowest number possible, right? Lowest number possible for simplicity, being able to find that lowest number possible so that I can truly understand and communicate where my substituents are. So in a ring, I like to start off with rings because you can really start anywhere in the ring. But if you want to find the lowest number possible, you're going to start counting where you see substituents. I could start here and go 1, 2, 3, 4. That's one way. That would be a 1 and a 4. I could do 1, 2, 3. That would be better, right? And then 4, 5. But here with this numbering system, starting with the ethyl, I'd have a 1 for the ethyl and a 3, 3 for my methyls. 1, 3, and 3 is not as good as a 1, 2, 3, 4, 5. This numbering system would say 1 methyl, 1 methyl, 3 ethyl. See how we're giving more ones? A 1, 1, 3 is better than the 1, 3, 3. Yeah? So now we got to put it all together. If I have two substituents that are the exact same name, my methyls, I get to call it a 1,1 dimethyl. The di, tri, tetra, if you have a tetra, you wouldn't. It would probably either be di or tri, and those are the only ones you do. So when you do assemble this complete name, we have a 1,1 dimethyl, and we have a 3 ethyl, and we have a cyclopentane. We're going to write the substituents first. To assemble the name, we want to write our substituents. So we put the number and the name of each substituent before the parent chain in alphabetical order. The prefix used in di, tri, tetra, if multiple substituents are identical, are ignored when alphabetizing. So the real thing that I want to use to alphabetize is my M for methyl, my E for ethyl. So when assembly, start with the substituents, 3 ethyl, 1, 1 dimethyl. Alphabetical order. E comes before M. I need both numbers of 1 because even though it seems redundant, it will work to help identify that there are 2 methyls and they're on the same carbon. Cyclopentane. Notice how this is all one word. We put dashes in between numbers and letters, and we put commas in between numbers. So identifying the parent, identify and name the substituents, number the parent chain to assign a carbon to each substituent, and make sure that it's the lowest number possible for those substituents. Try out all the areas that you can see. And then list the numbered substituents before the parent name in alphabetical order. We ignore di, tri, tetras, pentas, things like that. Excellent. All right. Once you get down naming, then we can move into conformations and looking at different molecules. Newman projections are the best way to observe a single bond rotation. Now, if you have your molecule kit, the best thing that we can do, and we'll play with one in class, and I'll hopefully have showed you before this how to make your own if you wanted, or which ones to purchase if you have to purchase. But single bonds can rotate. That's because they are a direct overlap of an atomic orbital that has the ability to rotate around the axis in the middle. And so there are multiple 3D shapes that we call conformations. A conformation is just being able to rotate a structure to move some bonds around. It's the same molecule, it's just looking at it in a couple of different ways. So a Newman projection is going to be the best way that we are able to actually observe the rotation around a sigma bond. And these are going to be mainly for alkanes that are acyclic, not in a ring. Now, we maybe have done a lot of wedge and dash ideas, right? Or skeletal structures. And that's great. Wedges and dashes showing the tetrahedral is awesome. There is something called the sawhorse, where just imagine starting to rotate around here so that we can start to view that center axis a little bit differently. It's like taking your sigma bond, this one right here, and starting to look down the sigma bond, not head on at the sigma bond like the wedge and dash. A Newman projection is when it's like we're a little stick person over here. There's me. And I'm looking down the sigma bond where there's one carbon in the front, that red carbon, and there's a carbon in the back, and that's going to be this carbon with the blue hydrogens. And so Newman projections are ideal for comparing the relative stabilities of specific conformations of a molecule. When we're looking at a Newman projection, we will be looking down one bond at a time, a specific carbon-carbon bond. So there's the disembodied eyeball right here. Ooh, scary. And it's looking down this bond right here. And so what we want to be able to do is draw the carbon in the front. And what does it look like? It has some hydrogens that are wedged and dashed on the top and one that's coming straight down. So let's draw that first. What that person or what that little eyeball sees is this front carbon, I'll just label it F. It's got a hydrogen in the front, on the two on the top and one on the bottom. Now the back carbon here has a hydrogen sticking straight up, and then the wedge and the dash hydrogens below. To draw the back carbon, we do a circle so that we can say, hey, here's the back. That's what is happening. That right up a little bit. Hydrogen sticking straight up and two hydrogens out to the side. This is a Newman projection. We have a front carbon and a back carbon, and we are visualizing the sigma bond that's in between this bond right here down the middle. And what we're really focused on is seeing how much space is in between the groups on each of those carbons. So looking at this, not necessarily of the bond itself, but how does the bond rotate the groups around it? So we're going to start off with very simple structures. We'll get into a little bit more complex things. But first, what we want to do is just be able to take a molecule and draw. This should be a chlorine. There. So I like to, at this point, draw in the hydrogens. If this is my little disembodied eyeball that's looking down this bond, I have hydrogens here and here, and I have one here as well. I like to note that because when we're looking at this, these hydrogens that are wedged are going off to the little eyeball's right-hand side. Pick yourself up and put yourself right where that little eyeball is and say, okay, if I have hydrogens coming out of the paper or out of my screen, that would be on the right-hand side of that little eyeball. The dashed CH3 and dashed H are going back into the screen, behind the screen, or behind whatever you're watching this on, and that is to the left of the eyeball. And then we also have this methyl and this chlorine, which should be opposite of each other. One's on top and one's on bottom. So drawing that front carbon and back carbon. Front carbon first. We have the Y. There's the front. There's two hydrogens. I'm going to color them how we had colored before. The right hydrogen and the left hydrogen. And what's down at the bottom? A CH3 group. I'm going to write in the CH3 just so that we can see it. Okay. Front carbon, done. Back carbon, do the circle. Now we have a chlorine that's sticking straight up. That chlorine should be on the opposite side of my methyl group, and it is. Excellent. And he has two other groups. Hydrogen is wedged coming out towards him, Methyl is dashed. What's important about a Newman projection is you write everything attached. Do not leave off groups. Do not just write C's. Do not just write H's. Do not just leave them blank. Write everything that's attached to each of those atoms. So this is how we would write a Newman projection given a specific orientation, right? So when we're looking at this guy, specifically down this bond, that is what we see. Try building it if you have a molecule kit and putting your eyeballs down the same path as this picture. A conformational analysis is really helpful to do when we are diving into Newman projections. The angle between atoms on adjacent carbons, so you're looking down a front and a back carbon, those are adjacent carbon atoms. And so the angle right there between those, the front hydrogens and the back hydrogens is called a dihedral angle or a torsional angle. It is 60 degrees on the molecule below. If we have a full piece of the pie that is 360 degrees, and we divide it into 6 pieces, that's 60 degrees. So each one of these is 60, 60, 60, 60, 60, 60. Excellent. So as we're looking at that dihedral angle, what's important to note is that I can rotate one of the carbons, either the front or the back. Dealer's choice, it doesn't matter. In your textbook, I believe they tend to rotate the front carbon. But again, pick one and rotate it. What happens when you rotate 60 degrees? What you are doing is you are turning one part of the sigma bond, rotating it along the axis of the sigma bond, which has free rotation. You can turn that all around and around and around like a little merry-go-round. We're going to turn at 60 degrees at a time until we reach the full 360 circle and get back to the beginning. The reason why we want to do this is because we see two different conformations now. We see a staggered and we see eclipsed. Staggered meaning that each hydrogen has space. We're kind of peekabooing. Here's the front ones, and the back are peekabooing in between. Eclipsed is exactly what it entails, the idea that we are hovering one hydrogen over the other. Now, staggered is lower in energy than eclipsed. The reason for this, main reason, is because of something called hyperconjugation, which we'll get to in just a little bit, but also the idea that there is more distance in between the hydrogens when they are staggered versus when they're eclipsing. They're bumping into each other. Electrons repel. And that increase of energy is what we call torsional strain here. It's the difference in energy between these two conformations. So when we go from staggered to eclipse, there is a difference in energy of 12 kilojoules per mole. And so we can look at that difference in energy and start to plot out the energy diagram of rotating. Now notice that we're starting here with the hydrogens on opposite sides. And as we start to rotate the front carbon, we rotate 60 degrees. We go from staggered up to eclipse, 12 kilojoules of energy, higher in energy. And then we'll rotate again back down to staggered. And notice how I've got those two hydrogens closer together. The bottom or the back carbon and the bottom hydrogen are not moving. The only thing that's moving is the front carbon. So that red hydrogen in the front is what we're trying to keep our eyes on. Each one of these staggered and eclipsed conformations is identical. Every 60 degrees rotation, we flip from staggered to eclipse, back to staggered, up to eclipse, back to staggered. And the difference between staggered and eclipsed is 12 kilojoules of energy. What that means in reality is it's possible that the eclipse conformation is 12 kilojoules less stable because of these two hydrogens and these two hydrogens and these two. The electrons in those bonds are closer together. So if the total cost is 12, that must mean each hydrogen costs 4 kilojoules per mole. There's 3 of them altogether, 3 eclipsing groups, and so 12 divided by 3 is 4. So eclipsing CH bonds, a CH bond on the front and a CH bond on the back, costs 4 kilojoules per mole. Excellent. So with this difference of 12 kilojoules per mole in stability at room temperature, 99% of the molecules will be staggered. The molecules don't like to rotate because it costs energy. It can rotate, especially if we heat things up or if we start a reaction. It can rotate for sure. But what's important is that it does cost energy. So another reason why this is important is the idea of hyperconjugation. Now, when we are staggered, notice this is back to our wedge and dash format. When we are staggered, when we have bonds that are opposites of each other, looking at a staggered position, why is staggered so much more stable? Partly because eclipsed positions have electrons that are closer together, electrons in 2 separate bonds. Eclipsing costs energy because of electron repulsion. Excellent. The other reason is because in staggered, we have something called hyperconjugation. Hyperconjugation is the idea that in a stabilizing interaction, a filled bonding orbital is parallel to an empty antibonding orbital or empty orbital in general. And so when we're looking at this diagram, notice that there's an overlap here. Now this is filled. There are 2 electrons here. This one is empty. And it's also antibonding. It's high in energy. These electrons in the filled bonding MO, the sigma bond between carbon and hydrogen on one side, is able to actually push some electron density into the antibonding orbital. Now the antibonding orbital is for this carbon-hydrogen bond right here, down here. This empty orbital is the space of antibonding that is empty. Remember when we talked about MO theory, for every sigma bond, there is a sigma star, and that sigma star should be empty. And right here, we can utilize that emptiness to spread out some of the electron density from another filled sigma bond. That hyperconjugation does not exist in the eclipsed format. Let's move up a little bit to propane real quick. Propane, our 3 carbon chain. So now what we see is we have a methyl group that we're trying to locate around as it rotates 60 degrees. Again, the only difference here between ethane and propane is 14 kilojoules per mole instead of what we saw before, which was 12. And so the big difference here is the barrier to rotate for propane being 14 means that there's a little bit something else going on. We know that a CH costs 4 kilojoules per mole. This one, 4 kilojoules per mole. So how much does this one cost? Well, 14 minus 4 minus 4 is 6 kilojoules per mole left over. So an eclipsed CH3 with H is 6 kilojoules per mole. costs a little bit more. Why? Well, a methyl group is bigger than a hydrogen. There's more electrons. There's 3 more bonds in that CH3 group. And so when we're looking at that, the HH eclipsing costs 4, but the CH3 to H eclipsing costs a little bit more because we're getting bigger atoms. And so we can start looking at a rotation, looking at a structure and being able to analyze that torsional strain and the cost for rotation of individual groups that are eclipsing. Again, remember, most often, not always, most often we do these calculations for eclipsed groups. Okay, let's go to butane, 4 carbons. Now again, we can see a couple of different things here. When the 2 methyl groups are spread out, we're looking down the carbon 2 to carbon 3 bond right there. In this conformational analysis, if we were to look down that bond, that's where our eyeball is. We see 2 different actual values here. When the methyl groups are opposite of each other, that is the lowest energy possible. This is actually called our anti-configuration, when the 2 biggest groups are farthest apart. They're on opposite sides. And notice if we rotate 60 degrees, we get an eclipse position that is 16 kilojoules per mole higher. That makes a little sense. We have 4, 6, and 6 for our cost of energy, right? 4 for the eclipsing hydrogens and 6 for each of the methyls eclipsing a hydrogen. And then when we rotate again, notice we're not at a lowest energy conformation. It is staggered, but it's staggered and it's called gauche because it's not the best. The methyl groups are actually still close together. And this is where a staggered position costs energy. It costs 3.8 kilojoules per mole. We'll talk about that in our chart at the very end, but what's important to note here is that even in a staggered conformation, you can have groups bumping into each other, and pushing those big groups together into this gauche staggered position is difficult for it. Rotate again, and we get our the worst or the highest energy position, which has the eclipsing methyl groups. This should be a lot of energy looking right there. We'll calculate that in just a second. 19 kilojoules per mole higher than our anti-staggered. We get another gauche, where the 2 methyl groups are still staggered but next to each other. And again, still 3.8 kilojoules here. Rotate again, we get our same 16 kilojoules difference in the eclipse, and then back down to our anti-staggered, which is the lowest energy conformation. Now, the stability difference between, let's just draw our anti and our gauche. Here's our anti, big groups opposite of each other. And I'll draw 1 gauche. And here is where there's some steric hindrance, there's some bumping into each other. And that is what costs 3.8 kilojoules per mole. And it costs that because those methyl groups are actually interacting. They're close enough that we can cause a little bit of what we call steric strain. Higher energy because the 2 big groups with a lot of bonds with more electrons, those electrons are closer together, and we know electrons repel. What about our highest energy conformation here? If we see these eclipsing groups, we know hydrogens eclipse at a cost of 4 kilojoules per mole. The total was 19, so minus those 2 4s. 11 kilojoules per mole for 2 methyls eclipsing. These numbers you do need to know. This chart right here is what I want you to know. The energy costs for eclipsing and gauche interactions can be used to give the approximate energy of a given conformation. We'll practice that a lot in class. Being able to draw the given conformation like we did last time, and then being able to analyze the eclipse position and the cost of it will be an important idea on your exam.